Bismillahirrahmanirrahim. In this tutorial, we'll talk about Graham's law of diffusion and Dalton's law of partial pressure as an extension to the ideal gas law, and that would help us describe relations between the gases as well. Okay, and we'll continue solving some problems from sheet 1. So first off, Graham's law of diffusion just states that the rate of diffusion, this R capital is the rate of diffusion, is inversely proportional with the density of the gas, or to be accurate, the square root of the density of that gas. Alright, so it basically says the heavier a gas is, the slower the diffusion for that gas would be, which is logical or makes sense. Okay, and if you remember from last time, we had Pm equals rho RT, and at the same conditions, pressure, temperature, and of course constant R, the molecular weight is directly proportional to the density. So we can also say that the rate of diffusion is inversely proportional with the square root of the molecular weight or the density, and just the proportionality constant here would be different. Okay. Alright, so if we have two different gases, we can describe the ratio between their diffusion rates, or maybe which gas is faster or has a faster diffusion than the other, just by dividing both relations. So this would be the rate of gas A over the rate of gas B would be square root of the density of gas B over density of gas A, or molecular weight of gas B over the molecular weight of gas A. Alright, and that's it. That's all we need to know about Graham's law of diffusion. So let's solve a couple of examples or questions here. The first question says two closed containers. One has hydrogen sulfide gas, H2S, is found in the first container, and in the second container, ammonia gas is found. Alright? And they are, the two containers are at the same distance from you and are opened at the same time, of course. Which gas will we smell first? And what's the diffusion rate of this gas, the faster gas, with respect to the other gas? So how much faster would it be than the other gas? Okay, so in this system, we'll just, let's say this is you, and you have two containers, and you're in the middle. This has H2S, and this has ammonia gas. Alright, so to do that, we can just calculate the molecular weights for both, and the one with the lighter molecular weight will be faster. So the rate of diffusion of ammonia will be faster than hydrogen sulfide. How much faster? We can just get the ratio as the rate of diffusion of ammonia in relation or in ratio to hydrogen sulfide will be the square root of their molecular weights, which is just 1.4. So the ammonia gas will be faster than hydrogen sulfide by 40%. Alright, next question. In an experiment to measure the diffusion rate at STP, standard temperature and pressure, for two gases, one of them is oxygen, so we know the first gas is oxygen, and it leaks at the rate of 15.7 milliliters per minute, while the other gas leaks at 10.6 milliliters per minute. Calculate the density of the other gas. So we have this other gas X. We don't know what gas it is, but we do know the rate of diffusion for that gas, which is milliliter per minute or number of moles per minute. It won't make a difference if we're just dividing both ratios or both rates. So we know that we need to calculate the density from this relation, and we already have the rate of diffusion for both gases. We just need to get this density of oxygen first to be able to calculate the density of gas X. So to calculate the density of oxygen, we can just use the ideal gas law in the form of molecular weight and density instead of volume and number of moles. And we have the pressure we have the R is of course constant, and the temperature at STP, and the molecular weight of oxygen is just 32. And we can calculate the density of oxygen, and then from the above rule we can just calculate the density of the other gas. And of course this needs to be bigger than the density of oxygen, since it's much slower in diffusion with respect to the oxygen. Okay. All right. Next question. A vessel containing nitrogen gas is leaking over a period of 13.5 minutes, resulting in a decrease in pressure in the container from 1800 millimeter mercury to 1200 millimeter mercury. When the same container was filled with another gas, a leakage of 15.5 minutes resulted in a pressure decrease for the same conditions from 1800 to 1200 millimeter mercury. Calculate the molecular weight of that gas. So this could be an experiment that we do in the lab. We get a container which has a constant volume, of course, at a certain temperature, and since we didn't mention anything about the temperature here, we'll assume that it's isothermal experiment, or at the same temperature. And we start with, let's say there is a pressure gauge in here, and let's start with a pressurized nitrogen gas or any gas at 1800. We might have a valve in here to release some gas, so we will open this valve and then measure the time on a stopwatch for the pressure to decrease from 1800 to 1200, and then we'll just close that valve again. Okay. And that time of diffusion will be the time of diffusion for a particular or a certain number of moles in there. Okay, if we get another gas, a gas X, which we don't know, but we subject it to the same exact conditions, so same starting pressure, temperature, and volume, and we open the valve again for the same container, and then let it release some gases until we reach 1200 on the pressure gauge, and then close the valve again, then we know that the same amount of gas was released over the time that we measured, right? Because in the ideal gas law, we don't care about the gas itself or the species, the chemical species. We only care about the parameters which are pressure, temperature, volume, and number of moles. So number of moles doesn't take into account anything about the gas itself. It's just number of moles of any gas would behave the same for all of the gases, assuming ideal behavior. Okay. So P1V equals N nitrogen 1 RT, and so on. This is for gas X and gas nitrogen. The same relations are valid. And then for the nitrogen gas at conditions 1, it's the same exact number of moles as gas X, since they both have the same starting pressure, temperature, and volume. So the number of moles at the start is constant, and the number of moles they both end up at is also the same. So we know that the delta N, or the released number of moles, is also the same. What do we get from this? We then can say, all right, so the number of moles released over the total time measured on the stopwatch is the same number of moles here over the time for the second stopwatch or for the second gas. All right, and since the number of moles is the same, we can just take them out both, and then we would have this relation at the end. So Tx over T nitrogen is equal to the square root of mx over m nitrogen, or molecular weights. And from this relation, we can just get the mx, which will be 36.5. Okay, next relation that we'll be discussing in this tutorial is Dalton's law of partial pressure. And what Dalton basically says is that the total pressure for a mixture of different gases is equal to the sum of all the partial pressures for each gas in that particular mixture. And the partial pressure, what is this partial pressure that Dalton is referring to in here? It's just the pressure of each gas that would be exerted, or the gas will exert that pressure if this particular gas in the mixture contains the or occupy the whole entire container by itself with no other gases in the mixture. So graphically representing this is that we have a container of volume V, and we have gas A, and this gas A inside that container, if it's present alone, so the pressure that we would measure for that container would be PA, which is the partial pressure for gas A since it's present alone. And if we insert a gas B into that container, so the pressure gauge will also be measuring the pressure, the partial pressure for B, if B is alone. And if both gases are present at the same time, this will be the total pressure, not PA or PB, but it will be the sum or the total of PA if it was present alone in that container, plus PB if it was present alone in that container. All right. So that's what Dalton is basically saying. All right. So the P total, or the total pressure, would be in general the summation of all the partial pressures for all the components inside a container or a certain mixture. And to get a partial pressure for any of the gases inside that mixture, we can just say from any two relations here, let's take relation 1 and relation 3 here, and divide them over each other. So we have P for any component over the total pressure is the number of moles for that particular component over the total number of moles. Or the partial pressure for any component is just the molar ratio, which is Y, molar fraction or molar ratio for that gas inside the mixture, times the total pressure to get only the partial pressure for that gas. Right? Okay. Next topic is the saturation pressure of water vapor. The saturation water vapor pressure at any temperature could be retrieved from relations or tables, just like this one that you'll find in the notes or the sheet. And it just depends on the temperature. The saturation pressure or vapor pressure depends on the amount of energy inside the liquid phase, and the temperature, as we discussed before, the temperature is the indicator for how much energy is inside a certain liquid. All right. So for higher temperature, the liquid will have more energy and will be able to exert more pressure. That's why we can see in here, as the temperature goes up, also the vapor pressure or the saturation pressure goes up as well. Okay. So what do we get from this? Any gas that's stored or present physically above a liquid surface, let's say this is water, and this is actually for any liquid, not just for water, but this table is particularly for water. All right. So any gas, let's say this gas X, the red gas, is present over the surface of or above the surface of water. It will always be, given the proper amount of time, it will always be saturated with the vapors of that liquid, because that liquid still has some energy to vaporize some of the liquid inside of it. How much? Just retrieve the temperature and pressure from the table. So at 30 degrees Celsius, the water liquid will be able to evaporate water until the partial pressure of the water vapor molecules in the gas mixture reaches 31.8 millimeter mercury. And that's the saturation pressure of water at that temperature in the gas above it. All right. Okay, let's see in a couple of questions or examples. It will be clearer as we go. So the first question for that part says, calculate the partial pressure of oxygen in an air sample having the following mass composition. okay, and this is mass composition or weight percent like last time. So we'll need, knowing that the air pressure is 1 atmosphere, we'll need to convert this into molar, right? We need this in molar instead of mass because all of the relations we're using are built for the molar quantities. So these are the givens. Just like last time, we've taken a basis of 100 grams, and as discussed last time, this can be any amount, the sample that we take, because we'll just need to know how many molecules or moles are present in that particular sample. So it's always a ratio. It won't matter if you take a bigger sample or a smaller sample. And then we get the number of moles just like last time. All right, so what do we need from this table? We need the molar fraction for oxygen, because the oxygen partial pressure will be the molar fraction of oxygen, this is Y oxygen, times the total pressure, which is 1 atmosphere. Okay, so to get the molar fraction for oxygen, we need the number of moles for oxygen over the total number of moles, and we can get the partial pressure for oxygen in this case, or in that question or conditions. Right, the second question says we have 176 milliliters of oxygen was collected over water at 30 degrees Celsius. Okay, since it's collected over water, so we have a surface of liquid water, and this liquid water will evaporate some of the water vapor into the mixture of gas, which in this case will be just the oxygen and the water vapor, until it reaches the saturation pressure for water vapor at that particular temperature, which is 30 degrees Celsius. And this is the total pressure for the entire mixture. Okay, calculate the dry oxygen volume at STP. So we know the standard temperature pressure, but in this case we cannot say. All right, so let's say P1 V1 equals N1 RT1, and then P2 V2 equals N2 RT2. And what we would normally do for questions of this type is just divide both and say, okay, since it's the same gas, oxygen, so the number of moles is constant, R is constant as well, so it will be P1 V1 equals T1 over P2 V2 and T2. And then from this expression, we would be tempted to get the new volume at STP. But there is just one problem here, that the total number of moles in the first case and the second case is not the same. Why is it not the same? Because we in the first case, we don't only have oxygen, we have oxygen plus or and water vapor moles saturated inside that gas mixture. So this temperature and pressure refer to, and volume refer to the entire mixture instead of just the oxygen molecules or moles in the container, right? So the first step we'll need to do is just separate out the oxygen separately from the water vapor and do all of our calculations on just the oxygen, not oxygen plus water vapor. Okay, so here's the system. The first container has oxygen and water vapor together, and from the table, you don't have to memorize these numbers, of course. From the table, we can get the water saturation pressure is almost 32 millimeter mercury. So the partial pressure for oxygen alone inside that gas mixture would be the total pressure minus the water vapor pressure, and we can get the partial pressure for oxygen. Okay, so P1 V1 equals N1 RT1 and so on for the second case, and from here we can just say V2 can be retrieved, since N1 and N2 and the R is constant. We can substitute and get everything we need. All right. Okay. Next question. It says a gas mixture containing 4.8 grams of oxygen and 7 grams of nitrogen at 30 degrees Celsius, and let's say this is temperature and this is pressure, right? Calculate the volume of this mixture and the partial pressure of all the components. Right, so this is the first part of the question. Then calculate the volume of this mixture above water. So if we take the same amount of gas for case A from that container and put it in another container where that container contains liquid water at the same temperature and pressure. So that other container will have the same temperature and pressure. We need to calculate the volume of the mixture, the new mixture, and the mass of water vapor that will be present as the saturation of water vapor inside the gas mixture. Okay, so let's split them into the first part of the question is part A, and the second part is part B. So let's focus on part A for now. Part A just says we have oxygen and nitrogen in a container at a certain pressure and temperature. So the total number of moles would be the mass of oxygen over the molecular weight of oxygen plus the mass of nitrogen over the molecular weight of nitrogen, and we get the total number of moles. The volume is just simply nRT over P. We can get the volume for that container, for that gas. And then the partial pressure for all the components will be molar fraction of that particular gas times the total pressure. And since this only contains oxygen and nitrogen, if we know the partial pressure of oxygen and the total pressure of the mixture, we can just get the nitrogen partial pressure by subtracting both. Okay, so that's for part A. It's very simple, just a direct substitution. For part B, we'll take the same amount, the 0.4, these are the 0.4 gram moles of the oxygen and nitrogen from part A, but we will introduce them into a new container that contains liquid water at the same temperature and pressure. Okay, so but this total pressure refers to the entire mixture. This is the entire pressure on the container itself. All right, not just the oxygen and nitrogen like in part A. So we need to get the volume of the mixture above that water surface and the mass of the water vapor present in the system or in the gas mixture. All right. Okay. Just like the last question, we cannot just use P1 V1 equals P2 V2 and say that the pressure or the temperature is constant and the number of moles is constant, because this time the number of moles changed in case 2 instead of in case 1. So what we need to do is first separate out the dry gas like we did last time, but the dry gas this time contains 2 compounds, not just one, but it's actually the same. So all we need to do is calculate the dry gas pressure, which is the total pressure minus the saturation pressure for water vapor in here, and we get the dry gas pressure. Then we can just use P1 V1 equals P2 V2 to get the total volume for the second container, this container. So the volume is actually the volume for each of these gases alone, because if we have a gas mixture, each compound or each gas in the mixture will occupy the entire volume of the container by itself, and not, for example, not split the container volume among the different gases. So this would be like O2, H2O, and N2. This is not what happens in reality, since the intermolecular distances between the molecules are very big in the case of gases. So the gases diffuse between each other and take up the entire volume of the mixture container by themselves. So this volume is the volume of the entire container and will be occupied by oxygen alone, nitrogen alone, water vapor alone, and the entire mixture as well. So when we try to calculate the water pressure or the number of moles inside this container for the water, we have PV equals nRT for water only to get the number of water molecules only. And the V in here is just the volume that we just calculated. Okay, so in this way we can get the total number of moles of water inside this container and simply to get the mass of the water present, we just multiply the number of moles of water times the molecular weight for water to get the number of grams inside this container. Okay? Next question. This question says, if the partial pressure of oxygen in air at atmospheric pressure is 156 millimeter mercury, calculate the mass fraction of oxygen in air. So we have the molar fraction, or the partial pressure. We can get the molar fraction for oxygen in air, and since it didn't say anything about the composition of the air, just as we agreed before, we can assume that air only contains oxygen and nitrogen, and as we can see here, it's 20.5% oxygen, 79.5% nitrogen. And in this question, it's actually the exact opposite of what we used to do. Here we have the mole fractions, or moles percent, and we want to get the mass fraction from the mole fraction. So instead of previously having to go this way from mass fraction to mole fraction, we are going that way from mole fraction to mass fraction. Okay, so these are the givens, the component and the mole fraction. Here we'll assume a sample of that gas like we did last time. Just this time it will be a sample of 100 moles instead of 100 grams, since we have the information for the mole percent, not the mass percent. Calculating the molecular weight and getting the mass for those 20.5 moles of oxygen in the 100 moles sample, and we can get the total mass for that particular sample. And since the ratios do not change when we take different sample sizes, it's always the same, because we'll divide the mass in that sample for gas X over the total mass, which will be always the same for any sample size. We can get the mass fraction of oxygen and the mass fraction of nitrogen. Next problem, 46 liters of oxygen were mixed with 12 liters of helium at 25 degrees Celsius and 1 atmosphere in a 5-liter container. Okay, calculate the partial pressure of the gas mixture components as well as the total pressure. So what's tricky about this question is that we have a volume of 46 liters of oxygen and 12 liters of helium at 25 degrees Celsius and 1 atmosphere pressure, and they are mixed into a 5-liter container. So it's counterintuitive at first. How do we mix two volumes that would result in like 58 liters of volume for the gas and put them inside a 5-liter container simply by compressing them into the container? Okay, so the temperature and pressure are actually for the inlet gases, and we will compress them and pressurize them to go into the 5-liter container at 25 degrees Celsius. Alright, so the first thing we do is get the number of moles for oxygen and for helium, and once we have the total number of moles of gas that needs to go into the 5-liter container, we can just get the total pressure inside the 5-liter container, nRT over V. We can get the total pressure, and as we see, it was pressurized to over 11 atmosphere to be able to take up the two components or compounds into this smaller volume. Okay, and to get the partial pressure for each of the gases, it's just simple substitution. We get the number of moles for each one over the total number of moles multiplied by the total pressure, and we can get their partial pressures inside the container. Okay, that's it for today's tutorial. Please let me know if you have any questions. See you next time.